Hello, my name is Bernard Schutz, and I'm a professor in the Gravity Exploration Institute here in Cardiff's School of Physics and Astronomy. In this institute, we research gravitational waves. The image behind me is of the huge LIGO gravitational wave detector in the state of Washington in the northwest of the USA. Its arms stretch out 4 kilometers from the central station. We're partners in this project, working in one of the most exciting fields of astronomy today. This LIGO detector made the first ever direct detection of gravitational waves in 2015, and since then has detected many dozens more. In Cardiff, some of our scientists work on the technologies in this and other detectors. Other scientists in our institute get the data from the detectors and work with colleagues around the world to analyze it, to understand the discoveries we're making about black holes, neutron stars, the expansion rate of the universe, the prehistory of our own solar system, and much more. The idea that gravity could have waves goes back a very long time. Newton conceived his famous law of gravity while he was self-isolating at his countryside home in 1665 to 1667. Avoiding a different epidemic than ours, England's bubonic plague. He kept his theory as simple as possible, and in particular, he assumed that gravity did not have a speed. As the planets orbit around the sun, their gravitational effects on one another change as their distances from one another change. And for Newton, this change happens instantaneously. However, many scientists in his day and later found this a hard idea to accept, and they speculated on what would happen if gravity had a finite speed, which would of course imply that its effects would ripple through space. But it took the genius of Einstein to put together in 1915 a full theory of gravity that obeyed the fundamental principle that nothing goes faster than light. In this theory, general relativity, the speed of gravity is exactly the speed of light. Gravitational waves travel at this speed, stretching and compressing space as they travel. But as soon as he worked out the physics of gravitational waves in his theory, Einstein understood that this stretching would be extremely tiny, and so he dismissed the idea of actually being able to detect them. That's because gravity is such a weak force. Think what's going on in this photo. The chemical forces in the muscles, in the arm and in the hand are defeating the pull of gravity on the apple by all the atoms in the entire Earth. Chemical forces are electrical forces, and it takes only a tiny mass of muscle chemistry to beat the gravity of the whole Earth. So when a wave of gravity passes by, its effects are going to be very small compared to the normal forces in a detector, making it hard even to notice the wave was there. Fast forward now from 1915 to 2015. Technology has improved beyond Einstein's imagination, and by pushing right to the frontier of what is possible to measure, we can now detect these waves, these very weak signals. And astronomy has also changed our view of the universe dramatically from what Einstein knew. We now know that the universe contains big black holes, lots of them. Some of them orbit one another and merge together, as shown in this supercomputer simulation. It uses full general relativity to predict what the waves emitted from such an event would be like. The black holes spiral together because they emit a lot of energy in gravitational waves. This loss of energy comes from the orbit, acting like friction on the motion. So they inevitably get closer and closer until they merge. I got into this research in the mid-1980s here in Cardiff, developing the methods to analyze the data and to do supercomputer simulations like the one you just saw. In Cardiff, We held the first ever international conference on data analysis for these detectors. And in 1990, we did the first tests of methods to analyze data, using data given to us by our colleagues in Glasgow and Munich who are operating small prototype detectors. Naturally, these prototypes were not going to detect anything, but we were able to demonstrate that our methods would find signals if we had data instead from the detectors like LIGO, which in 1990 were still only on the drawing board. It took a huge effort by over 1,000 scientists working worldwide to get from that drawing board to the two big detectors of LIGO and the big Virgo detector in Italy. But in 2015, it paid off. This is what that first detection looked like. A few cycles that are strong enough to be seen above the detector's noise. Strong because the black holes were so close to one another that they distort space immensely. But then they merge to form a big, much bigger black hole, and all goes quiet. The signal stops. Each hole was over 30 times the mass of our sun. The signal is all in the audio band, and here is what it sounds like. It lasts about 1/10 of a second, so listen carefully for the pop. This merger happened 1.2 billion years ago, which means the waves have traveled 1.2 billion light years to get here. During that journey, those waves have been spreading out in all directions, so that when they finally reached us, the incredible distortion of space near the black holes had been reduced to a tiny stretching that lasted that 1/10 of a second. But we noticed it. Since then, we've registered about 50 detections, most of them mergers of black holes, but not all events involve black holes. In 2017, we detected a pair of neutron stars merging together. Because these are stars, their merger resulted in a huge explosion, which was observed by astronomers using telescopes and satellites all around the world. It was the closest event that we've detected, only 1/10 the distance to our first detection. The excitement was immense. This gave astronomers a good view, and we've already learned a huge amount from their data. We learned, for example, that almost all the heavier elements in the periodic table are made in such mergers of neutron stars. The elements of which the Earth is made were created in events that took place long before the sun was formed. The lighter elements came from supernova explosions, and now we know that the heavier stuff came from neutron stars. Our galaxy, the Milky Way, is like a big mixing machine, where over time more and more stuff comes out of explosions and gets mixed into the gas of the galaxy, which then forms new stars. We are literally made of stardust, and some of that stardust needed gravitational waves even to come to existence. Now, LIGO and Virgo have recently been joined by a Japanese detector called Kagra, and a third identical LIGO detector is being built in India. So over the next 10 years, we are going to see a huge number of very interesting discoveries. But there will be even more. We are planning even larger detectors than LIGO. This is a drawing of the next European detector called the Einstein telescope, which will be underground and have 3 10-kilometer long arms. Scientists in our Gravity Exploration Institute are working on the new technologies needed for this right now. And we're also preparing to go into space to detect gravitational waves. Our ground-based detectors are limited to acoustic frequencies from a few hertz to a few kilohertz. In space, we can go to much lower frequencies in the gravitational waves that we observe, which allows us to detect waves that have come from much bigger things. Black holes, for example, of 1 million times the mass of our sun. We now know that such holes exist, and they sit at the centers of most galaxies. Our Milky Way's black hole is 4 million solar masses. The image here is of the black hole in the middle of a nearby galaxy called M87. The picture is a rendering of observations of this object by radio telescopes all around the Earth, a network called the Event Horizon Telescope. These nearby black holes really just sit quietly in the centers of their galaxies, but sometimes galaxies run into one another, and this brings their black holes together so that they eventually merge, giving off huge bursts of gravitational waves. This was more common earlier in the universe, so studying these mergers will teach us much about how galaxies formed in the first place, shortly after the Big Bang. This is the space detector now being developed by the European Space Agency to find the waves emitted when two of these massive black holes merge together. It is called LISA. The LISA stands for the Laser Interferometer Space Antenna. I was one of the first proposers of this detector, and for many years I led the data team developing its scientific justification. Now that it is an approved project, I've stepped back so that the younger generation of scientists here in Cardiff and elsewhere can get integrated into the project. The launch is planned 12 years from now, but a huge amount of work is going on right now on the instrumentation and in the preparation for analyzing the data. At Cardiff, we have 10 teaching staff in the Gravity Exploration Institute, and we contribute to the basic undergraduate physics and astronomy teaching, as well as teaching advanced courses in general relativity and in gravitational wave science and technology. The more than 20 postdocs and postgrads in our institute also help out with teaching and work alongside the many undergrads who are doing projects with us. So if you're interested in learning more about this frontier of science, come join us in Cardiff. Thank you.